Investigating the impact of preparation conditions and formulation on the accelerated stability of tretinoin (RA) loaded liposomes prepared by heating method. Raisin Soleiman Awad, Wasim Abdul Wahed, and Yasser Baitar. Objective: the aim of this study was to investigate the most appropriate ingredients and the ideal conditions for preparing a stable all-trans retinoic acid or tretinoin (RA) loaded liposome formulation with a high encapsulation efficiency intended for immediate application on the skin using a simple preparation method. Practical procedures and methods. The study was divided into 3 stages. Stage 1: the optimization of the preparation conditions. The formulas were prepared using a heating method. The effect of formula variables on liposome properties was investigated. Formula variables included phospholipid quantity, soybean L-alpha-phosphatidylcholine (SPC) was used during this stage. Water miscible solvent type. Temperature of adding the active substance. Stirring speed. Duration of homogenizing size with a sonicator. pH of phosphate buffer. Ionic strength of phosphate buffer. Liposome properties included mean hydrodynamic diameter Z average, zeta potential ZP, polydispersity index PDI, encapsulation efficiency EE%. All properties were measured before and after sonication. The formulations prepared at different values of pH and ionic strength of the phosphate buffer were left at room temperature for a period of time, and then the measurement of properties was repeated in addition to measurement of pH. Dynamic light scattering process (DLS) and the electrophoretic mobility process were used to determine the mean size and zeta potential, respectively, with a Malvern Zeta-Zeiser nano series. Polydispersity index, which indicates the homogeneity of particle size, was also obtained with a Malvern Zeta-Zeiser nano series. The total concentration and unentrapped concentration of tretinoin were determined spectrophotometrically at wavelength 352 nanometers to calculate the EE%. Acidified isopropyl alcohol was used as a blank. Based on the results at this stage, it was selected the conditions that exhibited the RA-loaded liposome properties, which expected to show the best stability with time. Stage 2: preparation of final formulas. According to the selected conditions at Stage 1, 6 liposome formulas, FS, were prepared. 3 types of phospholipid were used. Soybean L-alpha-phosphatidylcholine (SPC) was used to prepare F1 and F2. F3 was prepared with a hydrogenated soybean L-alpha-phosphatidylcholine (HSPC), whereas F4 was prepared with a 1,2-dimyristoyl (RAC) glycero 3-phosphocholine (DMPC). F5 and F6 were prepared by replacing 20% and 40% of SPC in the formula 2 with cholesterol, respectively. Stage 3: studying the accelerated stability of the final formulas. The final formulas, F1 to F7, were stored at 40 degrees C plus or minus 2 degrees C / 75% RH plus or minus 5% RH for 6 months. All properties of liposome particles were determined as Stage 1 except EE%, which was determined by a validated HPL. C method. Chromatographic separation was achieved in the reverse phase C18 column, EC250/4.6 nucleator 100 to 5 C18, Mescheri-Nagel, Germany, as a stationary phase, while the mobile phase was acetonitrile, T phase 0.01%, in a gradient elution mode in the ratios of 70 to 30, 65 to 35, 70 to 30 V/V4, 24/4 minute, respectively. Other parameters were flow rate 1 ml per minute, injection volume 20 ml, oven temperature 30 degrees Celsius, and wavelength 354 nanometers utilizing a PDA detector. Acetonitrile was used to dilute all standard and sample solutions. Results. Stage 1, after sonication, 100 mg of SPC showed the best homogeneity. PDI equals 0.459 plus or minus 0.044, and the highest zeta potential, -63.2 plus or minus 2.83. A slight difference in EE% was noticed between 3 amount, 100,150,200 mg of SPC. The formula that was prepared by adding 3% V/V of glycerol showed the most homogeneous size distribution. PDI equals 0.459 plus or minus 0.044, and the smallest mean size, 194.56 plus or minus 16.74 nm, which was located within the targeted range, 100 to 300 m. The lowest temperature, 30 degrees Celsius, showed both the smallest mean size, 194.56 plus or minus 16.74, and PDI, 0.459 plus or minus 0.044. Besides, there was no significant difference in EE% between three temperatures, 30 degrees Celsius, 45 degrees Celsius and 65 degrees Celsius. 1300 RPM showed a higher EE%, 87.27 plus or minus 3.38%, and a smaller mean size, 194.56 plus or minus 16.74, than 600 RPM. No significant difference in zeta potential was noticed. Stage 2. The mean size of prepared particles was within the targeted range, 100 to 300 nanometers, with 15 minutes of sonication, which also showed a relatively small decrease in EE%, 87.27 plus or minus 3.38%, and a high zeta potential, -63.2 plus or minus 2.83. pH equals 6.5 of phosphate buffer, 0.05 m showed the lowest change in pH with time and the highest EE%, 64.64 plus or minus 0.132%, and no significant change in both zeta potential and mean size was noticed with time. Substantial decrease in zeta potential and EE% was noticed by increasing the ionic strength. The lowest ionic strength, 0.025 m of phosphate buffer, pH equals 6.5, showed both the highest EE%, 79.98 plus or minus 0.044%, and zeta potential, -45.4 plus or minus 4.03. The mean size was also relatively stable with time. Stage 3. pH. By comparing F1 with F2, it was noticed that adding sodium cholesterol sulfate, SCS, had a negligible effect on the change of pH observed with time. HSBC, F3, and DMPC, F4, showed less noticeable change in pH with time in comparison with SPC, F2. By increasing the ratio of cholesterol, the change in pH became less noticeable. Mean diameter and zeta potential. Zeta potential decreased simultaneously with the decrease of pH in all formulas. SCS showed a positive effect on the stability of liposomes with time, since the F2 prepared with SCS showed less change in mean size in comparison with F1 prepared without SCS. The best stability of mean size was noticed with HSBC, F3, which has a phase transition temperature, Tm equals 50 to 60 degrees Celsius, higher than the storage temperature, 40 degrees Celsius, where it showed the lowest increase in mean size with time in comparison with SPC, F2, and DMPC, F4. By comparing F5 and F6, prepared with cholesterol 20%, 40%, respectively, with F2, prepared without cholesterol, no deficiency in the tendency of particles to fusion was observed, where the three formulas showed more noticeable fusion after 3 months. EE%. EE% was obviously lower in F4, DMPC, 56.52 plus or minus 0.81%, in comparison with F2 and F3. Adding sodium cholesterol sulfate to Formula 2 showed a slight decrease in EE% in comparison with F1. The total percentage, the liposome formulas, F1 to F6, didn't show a noticeable improvement in the stability of active substance in comparison with ethanolic solution, F7. F2 and F3 showed a little more improvement in the stability of active substance than F4. F2 and F5 showed a little more improvement in the stability of active substance than F6. Conclusion: the pH of buffer had a noticeable effect on the change of pH with time. The ionic strength of buffer had a noticeable effect on zeta potential and EE%. It is necessary to add a charge-inducing substance to a neutral phospholipid to improve its stability with time. The phospholipid that had a phase transition temperature, Tm, above the storage temperature was the best choice to improve the stability of particles and decrease the fusion of them with time and to prevent the leakage of the active substance without needing to add cholesterol. It is necessary to add cholesterol to phospholipid that had phase transition temperature, Tm, lower than the storage temperature to prevent the leakage of the active substance. Liposome formulations didn't show a significant improvement in the stability of active substance in comparing with ethanolic solution.
Thank you for watching this video. Please subscribe our channel for watch more scientific research videos.